All right, a recap of Chapter 1, Lesson 4. Seems like we have a lot of people coming in confused. Hopefully this video will clarify a few things that you guys are having troubles with. All right, example 1 is talking about just discuss the continuity of each function. When we're looking at this and somebody asked me, they said, well, is it kind of like the domain? It is very similar to the domain. Except sometimes we can have a hole in the graph that won't be in the domain and a graph's discontinuous there. We might have a jump discontinuity, which actually has a domain of all real numbers, but it might be discontinuous at that point. So we need to discuss it. It's not exactly like the domain, but it is very similar. See, for this problem right here, x can never be 0 in the denominator. If x can never be 0, that's not my domain. That's a vertical asymptote there. My graph is discontinuous at x equals 0. So let's take a look at that graph. Okay, so right here is the equation. Has a vertical asymptote at x equals 0, and that's where it's discontinuous. All right, the next equation, x squared minus 1 over x minus 1. See, that would simplify to just a plain x plus 1. The factor of x minus 1 would actually factor out and reduce out of the numerator. Remember, when it factors out and reduces, it's actually going to give you a hole in the graph. So what I'm talking about is going to look like this. So the function, I'm sorry, I'm trying to get it to where it won't be blurry. Okay, so the function of x squared minus 1 over x minus 1 would factor. The factor of x minus 1 would cancel. And remember, when it cancels, it gives you a hole in the graph. So we have a hole in the graph at x equals 1. X equals 1 is not in my domain. If it's not in the domain, there is no way it can be continuous then, because there's nothing there on the graph for it to be continuous. So again, in this situation, the domain and where is it continuous actually happens to be the same answer. Okay, the third one they gave us was this piecewise function. Now, the domain for this one is all real numbers. This is not always continuous. How we're going to know if that is continuous is only if you plug 0 into the top equation and it equals when you plug in 0 into the bottom equation. If I plug 0 into the top, I get 0 plus 1, which is 1. I plug 0 in the bottom, that's 0 plus 1 is also 1. Therefore, this graph would be continuous at x equals 0. That's the only point where it would even be discontinuous, because we have a part of a line, we have part of a parabola, and both of those are always continuous. So here's what that graph looked like. And again, that was because these two y values right here were both 1. If they were not both the same value, then this graph would have been discontinuous at 0, even though the domain was still all real numbers. So please understand, from this right here, less than or equal to 0, greater than 0 is domains all reals. If there had been a split in this graph right here, then we would have had it been discontinuous at that break. Okay, at that break, in that case, x is 0. And the last one here for this problem was y equals the sine of x. We know the graph of y equals sine of x is continuous. It's smooth, the curve, it goes on forever in both directions. Okay, the next concept was talking about the one-sided limits, in particular like when you get one of these semicircles. So the one-sided limits talking about the limit as x approaches negative 2 from the right. That answer would be 0. But from the left side, the domain doesn't even exist, so I can't have a limit from the left side. So again, the limit, that part of the graph, if I from the right or from the left, you have to have something there, or it has to be in the domain. If it's not even in the domain, you can't have a limit. So hopefully that'll help that part out. For these greatest integer functions, I at least wanted to introduce them to you because some of you may go on and take in future college classes. We are not going to do the greatest integers on our test, and I've not seen it on the final. So just get through those the best you can for the homework. We'll help you out with them if you need help. The next example was talking about the continuity on a closed interval. So again, this graph right here would be a semicircle looking like that, only the top half of the circle. So it's continuous. Where is it continuous? From negative 1 to 1. That happens to be the domain of this function as well. So you are correct in the sense that a lot of times the domain is where a graph is continuous, but it is not always the case. All right, the next one says applying the properties of continuity. So if I'm looking at f of x equals x plus the sine of x, x is always continuous for all real numbers. The sine of x is continuous for all real numbers. So this entire function would also be continuous for all real numbers. We have no holes, no jumps, no asymptotes. So that one is continuous forever. Again, the 3 over 3 times the tangent of x. So if we remember what our tangent of x graph looks like, I'm just going to draw this over here in our book. So the tangent of x The period would be pi divided by that coefficient of 1. So I know from here to here is a distance of pi. So this happens to be pi half, negative pi half. A tangent graph goes 0, asymptote. Remember, this is the first quadrant where the tangent is positive. Here's the other side of it. This graph has not been shifted anywhere. Okay, this would be pi half plus another, because remember, the full period was pi. So if this is pi half plus 1 pi, that would put this at 3 pi halves. So here's the next part of that graph. Then 3 would have just changed the steepness and made it 3 times as steep. So basically between the 0 and the asymptote, this right here would be at a value of 3 is what that's telling me. And then negative 3 here. Okay. So what we're supposed to answer here is it's asking you about the properties of the continuity. See, this graph is continuous everywhere except for every time you see an odd number times pi over 2. So all the odd numbers times pi over 2 is where this graph is always continuous. I'm sorry, discontinuous, my bad. That point, those right there are infinite discontinuity. Those are your asymptotes. Alrighty, this third function, y equals x squared plus 1. I can plug anything into the numerator. That is a smooth continuous curve. The denominator was the cosine of x. Remember, the denominator cannot be 0. That's where it's going to be discontinuous. So if I was to take a look at the cosine of x graph and answer everywhere it's 0 is where this graph is discontinuous. The graph is continuous everywhere else. So the cosine of graph, if we remember, the period would be 2 pi divided by the coefficient of x. So that would be 2 pi divided by 1, which is 2 pi. The midpoint of that would be pi, and here was my 0, starting at the value of a. So I have it equal to 0 at pi half, and then again at 3 pi half. And so that's 1 pi half, 3 pi halves, 5 pi halves, 7 pi halves. So again, this is going to be the odd numbers times pi over 2. That's where this function would be discontinuous. It's continuous everywhere else. The next one we wanted to know, again, describe the intervals for which a function is continuous. So this main lesson really was about it being continuous, or where is it discontinuous. So again, this would be looking at the graph of the tangent of x. So I'll do that again in case you're kind of weak there. The period would be pi divided by 1. So over here in the margin, I'm going to go and draw that graph. So pi divided by 1. So the distance from here to here between the two asymptotes, that's a full period, has to be pi. So this is negative pi half to positive pi half. Again, the first quadrant, that tangent's going to be positive down here. So I'm going to have an asymptote at negative pi half, and then pi half, 3 pi halves, 5 pi halves, all those odd times pi halves. And that's how they wrote their answer right there, because it wanted to know the intervals for where it was continuous. See, it's discontinuous at all these odd numbers times pi halves. So they just did a little pattern there with the ellipses at the end of each one. Okay, for B and C, I'm not really worried about ones like this in your homework. These two here, you saw in the notes on the other one, they kind of did the squeeze theorem, and they did this where it's oscillating. So just kind of try to read through those, see if you can get through them. I'm not going to put that on my test. I haven't seen it on the final exam either. All right, intermediate value theorem, I do put on my test, and I'm going to point out a couple things the students miss on that. So first off, there has to be a couple things that have to happen for it. The intermediate value theorem must be continuous on the interval they give you. First off, if it's not continuous on the interval that they give you, you're done. You can't apply it. The next thing that happens is the f of a, they're saying cannot equal the f of b. That means the endpoints of the graph. And then it's saying we have to have a number k in between them. Then there exists at least one c in that interval such that f of c equals k. So we'll talk about the key points on this. So again, the curve had to be smooth and continuous. Okay, so if I have this function here, y equals x to the third plus 2x minus 1. That's definitely smooth and continuous. The domain is all real, but really what I'm looking for, is it continuous on this interval? Well, it definitely is. If it's continuous for all real numbers, then it's continuous from 0 to 1. The next thing I need to be concerned with then is what does f of 0 equal and what does f of 1 equal? Well, when you plug in the 0, you happen to get f of 0 to equal negative 1. And you get f of 1 to equal 2. So that's what we get. Now we're asked, can we show that this polynomial has a 0 in the interval from 0 to 1? See, is 0 somewhere between these two y values? And hopefully you're saying yes. So since it's somewhere between those two y values, then I know there exists a number between 0 and 1 such that my function will equal 0. That's all it's saying. See, if my graph is smooth and continuous, I have a point here at 0, -1. We have a point here at, I'm trying to get this plot, sorry, at 1, 2. And my graph was smooth and continuous. This graph has to cross somewhere between here at least once. Now, it might cross more than once, but it has to cross at least once. And that's what I need to find, is what is that value? So then I set my equation, my original equation, equal to 0 to find that value of C. All right, so again, like I said, that was your chapter 1.4 recap. If there's some other stuff that I need to recap on, just let me know. You guys, I hope this helps you out. Bye.